Okay, so next up we have Claire Merriman, and she will be talking about changing the rules for continued fraction expansions and their natural extension domains.
Okay, so thank you to organizers for inviting me and putting all of this together. And also for our first speaker for really setting this up quite nicely. So I will explain what is going on in these animations. You can kind of think of that as one of our goals of this talk. So in order to be a little bit animation friendly and ability to write on this, we're gonna deal with the fact that transitions between slides is a little funny. So I guess we will revisit, for those of you who are at the first talk, we will revisit the regular continued fractions, and then talk about what happens when we restrict to odd denominators, and then how Boca and I extended this to an entire family of continued fractions, which is what's going on in these animations, and also natural extensions. So once you get out of the kind of regular continued fraction case, natural extensions become a very useful tool because invertible things are nice to study. So we didn't see this presentation of continued fractions the last talk, so that's good. This is the Euclidean algorithm way of generating continued fractions. So you take some positive number, you find the largest integer less than it, and then you write x as that integer plus some error term. If our error is between 0 and 1 over that error is going to be less than 1. And then we can keep going, 1 over there is greater than 1, so we can keep going. We do this again, we get some new error term, and we can continue this process potentially indefinitely. And as just a reminder, this is fairly standard notation to just write out a list of what we call the digits so that it doesn't take up too much space, right? This is getting very big, very fast. And this process terminates if and only if x is rational. We have some issues with ambiguity, but we can kind of easily deal with that. I mean, this is a dynamics conference, so one way to deal with it is you just say the rationals are measure 0, whatever. The other thing you can do is just impose a rule and say, we don't want this case to happen. We'll just ignore it. And then we have uniqueness for every positive real number. And we can get shift maps by playing around with 1 over these expansions. So we get nice algebraic properties, but this is a dynamics conference, so we want to define these as a map. So those of you who are at the first talk, we did just see this. I use T partly because I call the golden ratio G, so we're going to use T for the Gauss map, which is we take the fractional part of x. This is the only place I'm going to be careful about not dividing by 0. Anytime you would divide by 0, just define your map to be 0. But the way we can think of this as generating the continued fractions is if we look at, instead of writing it as the floor of 1 over x, we just write it as some integer and think of what interval we're in. And in that way, we can just iterate this map and keep track of what we subtracted each time to generate the continued fraction expansion. If we stick in the continued fraction expansion, we just delete the first digit. So this is an infinite to 1 map. We did see in the first talk that you can study it just fine. Gauss studied it this way. But one nice tool is this invertible natural extension, which appears to have first been, I think, Nakata Ito, not just Nakata. I think it was the 77 paper, where this kind of popped in as a tool. And we do the same thing. We just put the Gauss map in our x coordinate. And then on each branch, the y coordinate is the inverse. So what this means for our, let's get a better color, continued fractions is we take this first digit of x and move it to become the first digit of y. So we kind of think of this is your non-standard, it's not the Rohlen way of defining the natural extension, but this we think of as the future, and this part as the past of x. And that's kind of in the continued fraction world, a standard way of defining these maps. And the dynamical system for both of these is ergodic. We get the standard Gauss measure, which is dx for x plus 1. And for the natural extension, you get this thing that integrates to over 0, 1 to that map. But this is really nice. This turns out to be far more general than just this case, that we can get things that look like that. So what happens for odd? So what if instead of rounding down in the Euclidean algorithm, we want odd integers? There's two kind of immediate questions. There turns out to be more questions, but two immediate questions is, what about evens? And the somewhat unsatisfying answer is make a choice and be consistent. We will eventually have a little bit better decision there, but that's what we have there. And then how do we get all positive real numbers? This one's a little bit easier to fix. Here we just say we can also subtract errors, which means plus or minus 1 as numerators. So let's look at an example, because I think that's going to be the best way to do this. If we start with some rational that I pick here, we see that it's between 2 and 3. Well, that means that instead of going to 2, which is what we were doing in the regular continued fraction case, now we round up to 3, which means we have to subtract our error. And then again, we repeat this process. So we have, we now have 13 over 3 in our denominator, which is between 4 and 5. Again, we round up and subtract our error. Which again, we're going to end up now, right? We are between 1 and 2, so we round down finally and add. And now we get that our error is 1/2. So this is where we run into the ambiguity, but we would have run into ambiguity in the regular continued fractions as well. So we have these two choices, and we end up having different cases where we use both. So this case is what we kind of standardly call the odd continued fractions. And this is what Rieger so kindly named the grotesque continued fractions. And what we're going to do is end up interpolating between these two and then trying to extend that. So yes, in the regular case, we just impose a rule and say which one we're using. Right, we just said, okay, don't do the 1 as your last digit. We could do that here, but we have a bigger problem than rational numbers. which is that we also have irrational numbers where we no longer have a unique continued fraction expansion. Where again, this one is going to be the first thing I define, which is the odd, and this one will be the grotesque. And I've been told that in German, grotesque maybe doesn't have quite the same connotation as in English, but that's what Rieger named them. They're not really that bad. So let's get back to dynamical systems. So if you have seen the odd continued fractions, yes, I am using slightly different indexing. I am making it consistent with the grotesque continued fractions and also the Nakata continued fractions. So what we have here is we restrict our digits to being odd, and we allow addition and subtraction. And then the way we handle this uniqueness is that any pair like this must add to 2 or greater. So you can't get 0. And that deals with a uniqueness enough there. And that, yeah, so that takes care of uniqueness. And we want continued fractions. So similarly to how the Gauss map just says an interval, this is what we subtract. That's what we're going to do here. And we define our interval now as 1 over an even integer and then the previous even integer in absolute values. And yes, we should be a little bit concerned about k equals 0. So we should intersect it with the actual interval we're studying. And one thing we can see here is that we do not get the digit 1 followed by a negative number because 2k plus 1 is 1 when x is in 1, or absolute value of x is in 1/2 1. So t odd, that's actually an O, of x is going to be positive. If you just plug in the values, you'll see you end up between 0 and 1. So that takes care or explains why 1 is never followed by subtraction. Another thing we can do here, I'll zoom in for a second, is actually graph it and look at what happens. So it's the same thing. This map, or this branch here and this branch here are positive, and you can look at exactly what the digits are going to be on those branches. Sorry, the labels were a little small. And again, you plug in your digits and the map just chops off the first digit. Our other option is the grotesque continued fractions, which is now this pair of digits. So have to be greater than or equal to, add to greater than or equal to 2. So it's what turns out to be the dual criterion. So this means that we get 1 or -1 over 1 only for the odds, and we get 1 subtracting something only for the grotesque. And then this can be greater than 1, right? 1, if you subtract 1 minus something and then divide by that, you can end up greater than 1. So that explains a little bit why our domain is going to shift now. So we go from the golden ratio -2 up to the golden ratio. So it's still length 2. It's just a different length 2 interval. And we do something very similar, but we've changed our definition of the interval. But again, we iterate and just keep track of the signs and what we subtract every time to get all of the digits. But our intervals are very different. It looks like this now. And you can actually see that we have a full branch here for the 3 minus 1. Let me scroll so it shows up. 1 minus 1 would be on minus g minus 2. So that's not in our domain. That also helps explain why we don't get that digit from a dynamical system standpoint. So what are we doing? These are dual continued fraction expansions. The way I like to see that is that we've kind of switched what that digit restriction is between the two. One is the denominator and then what the next numerator was, and the other one is numerator and the next denominator. There's a bunch of ways to define that as the dual, but that's one of them. We are going to define a way to interpolate between them. We want to then find invariant measures and natural extensions, because once you start doing that, the invertible becomes a really, really nice tool to have. And then try to extend these results. So we've extended them some. So the rest of this is based on a paper with Boca. And then the animations, which will start reappearing, is based on an undergrad research project we ran 2 years ago with undergrads Xavier Ding, Gustav Jennetten, and Joel Rozhon, who I believe are all still undergraduates at Illinois. So the first thing I want to do is just compare these two maps we've seen. If we ignore what those intervals are, these are fairly similar. We have 1 over the absolute value of x minus some odd integer, and it deletes the first digit. And then if we actually look at them as maps, right, our interval, the entire domain is different, and our rules for choosing what the odd integer is different. So here we have +2, here we have +1 plus g, and then there's a hidden +0 and -1 plus z here, or plus g. And then the digit restrictions are different. But we can kind of see some generalizing going on here. So we can define this new map of a length to interval for some parameter, where we have the same thing, 1 over the absolute value of x minus some odd integer, and we have some rules for picking that odd integer. So t sub o is phi sub 1, right? So if alpha equals 1, this agrees with the odds or the extended odds, and t grotesque is going to be when alpha equals g. So from there, now maybe, there we go. It's a little bit grainy in notability for some reason. This is actually as we decrease alpha and only plot as many branches as doesn't make Mathematica cranky. So yeah, some of them are missing because of Mathematica issues. Kind of what happens, and what you see is over on, this is probably gonna pause it, yep. Over here, we start deleting branches, and the Mathematica issue is that this branch just grows, but there is like memory issues of it getting cranky for that. But in general, now I told you we'll figure out what alpha is. Alpha is going to be between the smaller golden ratio and the larger golden ratio. we'd like to extend that interval, but right now this is what we have results for. And then this is exactly what I had on the previous page, where we define our interval as 2k plus 1 plus alpha and 2k minus 1 plus alpha. And again, we iterate to find these digits of the continued fraction expansion, where we look at the sign and what we subtract every time. We're not going to go into the really large amount of number theory of showing that you get convergence and everything. You do. And again, we just delete this first digit. So now we have this whole family where things work fairly similarly to what we had before. But if you want to extend things to ergodic theory results, invertibility is going to be a really nice tool. So, oh, wait, no, we need digit restrictions first. We also can find some patterns of what's happening here that do end up being helpful in the proofs that I'm not going to show you. So this is another way of stating that interval that really emphasizes what the alpha is, so that now we can use one notation for any alpha in this interval for the first digit. So this becomes its own map that you iterate. So in the case we have here, except for on the endpoints, we have that the first digit of alpha is 1 and the first digit of alpha minus 2 is also 1 in absolute values. Right, one of these is positive and the other is negative. And that if we iterate that map once, we just take phi alpha of both of the endpoints and add their reciprocals, you get minus 2. And yeah, we have to leave 1 out because that 1 minus 1 is 0, and we don't want to divide by 0. We also get descriptions of what cylinder set defies, well, not what cylinder set, but a limit on what cylinder set defies end up in, that break in the two cases. So there are a couple key things here. We've switched which one is greater than the other between the two cases, which has the effect of switching whether we add or subtract when finding the second digit. And then in both cases, if you apply phi twice to both endpoints of the interval, you get the same numbers. So we have here alpha is 1 over 1 plus 1 over d alpha. I'm just going to put squared. Plus phi squared alpha of alpha, and alpha minus 2 is, well, negative, and then we subtract 2, but this is now the same for the rest of it. Oops. And then the only difference here would be adding that 2. So that's going to play into what these, when we do define the natural extension, what the domains look like. So to define a natural extension here, we're going to define a map on some two-dimensional set here. I have intentionally not told you what it is yet, where looking at the continued fraction expansion, we move with this skew shift, which is partly because the measures behave better this way and partly because historically it's been done this way. But when we do this, we take this digit, and when we move it to the y, it becomes skewed like this. And this is one way to see the dual. So if we have a restriction on epsilon 1 over a1, that will be translated into a restriction on y with this skew shift. And we do the analogous idea to what we did with the regular continued fractions, which is that we put the Gauss map in our x coordinate, and then on each branch of the Gauss map, this is your inverse. So we get that future past construction of the natural extension. So if we go back to the two examples we had, the grotesque continued fractions actually behave pretty nicely this way. So here we had, right, this has to add to epsilon greater than or equal to 2. And now here we have that this, again, has to be greater than or equal to 2. So we've gone from the grotesque to the odd, and we've just kind of slapped some absolute values on and re-indexed. Which is why things are fairly nice here. And here alpha is the golden ratio. They are not as nice for the odds. And part of that is if you do try to do that same idea of, well, now I've defined this has to add to greater than or equal to 2. Well, that means that, like, I mean, it's not in here, but like this and this have to add to greater than or equal to 2. Right, it does eventually come out as the grotesque, but you have to like do a couple of iterates to see it. But the real thing that's going on here is, right, I said just throw absolute values on it. When you do that, it folds funny. So we can already see, looking at the extended odds, that our domains might be a little funny. And in fact, I'm looking, I have like 3 minutes. We're kind of fine here. So this is decreasing from the golden ratio. This, oh, no, didn't pause. Okay, when they line up, that's alpha equals 1. And then things get fractal. So I will say that is why we stop where we stop and with current results. But in the two cases I've defined so far, we actually do know what's going on. So you end up having phi of alpha minus 2 and phi of alpha being the endpoints of the top two rectangles. And so it matters which one is greater or less than the other one. And you get these 3 rectangles up to sets of measure 0. Your boundary points are a little bit more complicated to work with. But we get something like this. So in this case, things are pretty nice. I mean, the proof is gross, but you get 3 rectangles. And the key thing here is that these endpoints are the same, and we believe the next step where having those second iterates not equal to each other is part of what's going on with the fractal behavior. Part of, not all, but part of. So if we put them next to each other, this is what happens. So as we lose that first branch or first cylinder set, things start getting more and more fractal. So in the last minute, just want to make sure we do get back to the ergodic theory. You can find the measure for the natural extension is going to be, right, I said this was generally true. We get back to this measure with a different weight for the natural extension. You can then integrate that and find the measure for the just the actual Gauss maps, but it's defined piecewise, and like took up an entire slide just to show you what it is. So I'll leave it as you can do the integral or look at the paper to find it. Ooh, that didn't get, that's a tech typo, but right? We've proved this is in fact a natural extension. Even though it's a standard construction, you do have to prove that. And again, this should be an alpha. We get the natural, or that the map we started with is ergodic, exact, mixing of all orders. So we do get a lot of these kind of classic results. And then this is my last slide, which is a little bit of number theory. So we get all of these kind of standard different weights, but you can get limit results and entropy results and stuff as well. With all of this. So yeah, things haven't broken too badly, even though we have non-convex domains. And that is the end and time.
Okay, so let's thank Claire. We can unmute ourselves and. Okay, any questions for Claire?
Claire, I have a question. So in these, at least in the nice cases where you get a limit set or the domain of the natural extension is just those 3 rectangles.
Yes.
Is there some like short summary of like how the natural extension acts on this domain, like in terms of those rectangles? Like, is it easy to see, or is it like extremely complicated?
So I don't remember exactly off the top of my head, but it's not actually that bad. So for most of it, it just ends up interlacing the same way you would get, well, it's more interlacing than you would get for the regular continued fractions. And then I believe it's like this chunk kind of gets sent to itself. I could find it's in the paper, but yeah, it's like you divide it into chunks that kind of stay within themselves. And so while I define these as 3 rectangles, I think for actually how the natural extension domain works, our correct view is like this and this being a section. There's like 7 sections. You actually divide them vertically and not horizontally. And then I think I can just pull up the paper in a second. But yeah, there is a nice way. I just don't remember exactly.
Sure. Yeah.
I think it's this corner one that behaves funky.
I mean, maybe it's worth saying that, I mean, it depends on what you mean by complicated, right? Because the continued fraction map already is super complicated. And so, you know, the natural extension, whatever you're going to do is going to be this, you'll have one side, you have this countable branches. I mean, and I think it can't be that one of the rectangles goes to itself, because then that would
violate the
periodicity of the natural extension, right? It has to sort of spread across and in this kind of crazy branched way. So I mean, to me, all of these maps are very complicated.
Yeah, there's some like
say so much about them.
Complicated interlacing. I think just some of the interlacing is worse than others. Of like you turn vertical slices into horizontal slices is one thing that's happening here. And then yeah, like this whole Baker map style interlacing is going on. So kind of, but yeah, like Jaidev said, there's the whole, also it's ergodic, so only so much is behaving. But I think it's, yeah, you slice it vertically. I think one of these we had 7 sets that we analyzed case-wise, and the other one like subdivided. I think this one we ended up then having to subdivide those 7 sets into some of them into more sets.
So could I ask you a question about how, I think, Claire, you probably know the question I'm going to ask already, which is so these are beautiful natural extension domains for these kind of alpha continued fractions. Can you think about this? How do these relate to these cross sections that I think, I want to say Pierre Arnoux and Tom Schmidt have built to the alpha continued or the Nakata continued fractions in sort of the homogeneous space SL2R mod SL2Z, right? There should be some relationship. Do you guys have an idea of how these things sort of fit together?
I agree that there is one, and that would certainly be a next step. I mean, I've emailed a little bit with Tom Schmidt about it, and I think some of it follows some of the arguments work almost immediately for their cross sections because it's really just thinking about things symbolically, and parity restrictions doesn't mess with the symbolics. Some of it's less immediate. But I mean, to get anytime we get outside of this nice not fractal behavior, we're going to need new methods, and that's certainly a direction to move. It's not the direction I've been working on recently, but I am a little bit partial to Krijkamp's methods of the Nakata alpha continued fractions. I like his thought process, especially if you're going to look at things like digit restrictions. I think.
No, then absolutely makes sense to be sort of more common. I'm just thinking from a bigger picture perspective. It would be nice to sort of tie these two stories together, and I think that might be something very fun.
Yeah.
How it all fits together.
I agree. I mean, this is very much a first step in the project. And that is a kind of certainly a reasonable question that Pierre Arnoux and Tom Schmidt have asked.
Okay, so any more questions for Claire? Okay, if not, then there will still be sometime in the afternoon during lunch. You can talk to Claire and the other speakers. So maybe we can thank Claire again